All right. Hi, everyone, boys and Vera. I'm doing number 17. Okay. So I'm looking back at my notes, boys and Vera, and I have to say this, that I'm looking at the notes because I always kind of do a little noting after every one of my classes of what I do in class and what I cover. And I have to say, I'm looking here at linear algebra and I'm noting what I talked about and I'm noting the homework that I assigned. It can't have been, it really can't have been every single day. That can't be right. So if anyone could give me, and I'm looking for honest feedback, I'm not looking for histrionics or exaggeration. Is it every single day? Is it only the vector space stuff? I don't know. I'm still at a little bit of a loss. I will say to you, this most recent class and span, it sounds like, and now that I look at my notes, I did go through only 2 examples with you on span. So I can see how the homework may have been a little bit challenging. But please, if you are willing to give me some feedback about prior experiences thus far, I'm looking here, I don't think it's been every day. I don't think it's even been half the days, actually, now that I look at it. In any event, I would like to know, okay? All right, so here we are. Number 17, I just wrote this down, but it says they're just giving you a set, and S is the set of all continuous functions, and they're just calling the set all continuous functions vector f that they're naming f of x, such that the definite integral from a to b of f of x dx equals 0. Okay, so this is the set that we are going to be testing, right? And the question is this set a subspace of, and of course, we only talk about subspaces of vector spaces, right? So is S a subspace of the vector space defined as the set of all continuous functions? And I think they may have used this notation, C on A to B, I think. So this just means the set of all continuous functions over that interval from A to B, right? So the vector space is defined as the set of all continuous functions on the interval of x from A to B, right? The question here is this a subspace? Well, actually, this doesn't have to do with span at all. This is just subspace. Well, let's just go ahead and do it. So to determine if a subset is a subspace, let's look at axiom 1. Axiom 1 says that U plus V has to be an element of S, right? That axiom 1 says if I have any arbitrary member of S, which we call U, and another arbitrary member that we call V, if I add them together, will I have an output that is within that set, all right? Well, here, U and V are actually functions. So U I'm going to call a function such that the definite integral from A to B of f of x dx equals 0, because that is how a member is defined, right? See? F of x such that And I need a second member. Let's call the second member V, which is equal to g of x. And that second member is g of x such that the definite integral from a to b of g of x dx equals 0. So axiom 1 says that U plus V has to be an element of set S. Okay, well, let's see. If I do U plus V, in this context, that equals f of x plus g of x, okay? And then the question is, f of x plus g of x, will this yield, if I, again, take this function, will this be, does this equal, question mark, the definite integral from a to b of some continuous function, which is f of x plus g of x dx, does that equal 0, right? So the question is, will U plus V yield a continuous function such that the integral from a to b f of x equals 0, given U and V here? Well, let's see. F of x plus g of x, let's flesh this integral out. The definite integral from a to b of f of x dx plus the definite integral from a to b of g of x dx. And of course, we know from the given information here, this is 0 plus 0, which equals 0. So axiom 1 has been met because the function u plus v, such that right? This does in fact equal 0. So u plus v is in the set of continuous functions, that continuous function being f of x plus g of x, such that it yields a definite integral over that interval equal to 0. Axiom 1 has been met. Let's check axiom 6. Now that I think about this question is not on span at all. It's on subspace. So why did we have difficulty with it on the span homework, boys and Vera? I don't know. Axiom 6 says that k times u of x, u has to be an element of S, right? That k times u has to exist in that set that we are testing. Well, in this context, k times u equals, what did I call u? F of x equals k times f of x. Okay? And let's take a look. What will this be? Is k times f of x going to yield a definite integral where the definite integral over that interval a to b, does it equal 0? Okay, well, let's see. We know this is the case. And we know that this is a given. And we know that any scalar factor k times 0 equals 0. So we've just shown, that k times u is an element of that set. If I were to go over here and say, here I have shown that u plus v stays within that subset. Okay? Everyone all right? Okay, axiom 1, 6, 4, and 5, right? Okay, here we go. 4. Axiom 4 says, why don't you try axiom 4 on your own and then replay me to see how you did, okay? Go ahead and try that. Okay, so here's axiom 4, everyone. The question is there a 0 vector that exists in set S such that the 0 vector plus u equals just u? So all I said here was let vector u just be the number 0, whereby the definite integral from a to b of 0 equals 0. If that's the case, 0 plus u, or 0 plus f of x, which is really this plus this. Now again, please don't be literal and say that I am calling f of x this, okay? I'm just saying 0 plus f of x, and you know what? I can even say whereby. How about that? All right. Because I used the word whereby here, I think, or such that, right? Okay. 0 plus f of x such that, right? 0, the definite integral from a to b of 0 dx plus definite integral of a to b of f of x dx, this will just equal 0, right? Plus the definite integral from a to b of f of x dx, where f of x was defined as u. Okay, so the point is that in this case, if I let 0 be this integrand, the definite integral from a to b of 0 dx just equals, added to the definite integral from a to b of f of x, just gives you what you started out with, which was how we defined u. Okay? And finally, axiom 6, or no, let's see, axiom 5, right? Axiom 5. Is there a negative u? Okay, well, let's see. Negative u, let's define it. U is equal to f of x, right? Where the definite integral from a to b of f of x dx equals 0. By extension, negative u would equal negative f of x, where definite integral from a to b of negative f of x dx equals 0. The question is, does u plus negative u equal 0? Well, let's see. This we know equals 0. What does this equal? Oh, whoops, actually, we don't know that equals 0 yet. Let's do that. Okay, what does this equal? This is going to equal, let's pull the scalar out, negative integral from a to b of f of x dx. And we know that this portion of the integrand equals 0, negative 0, or just 0. So therefore, we have shown that there is an element in this space where u plus negative u equals 0. S is then a subspace of C. Okay? All right, very good. Maybe I'll do out the span question, I think, on the problem set. Where is that one? On your attached problem set. Go ahead and pull that one up. It's the span, I think, of e to the negative 5x and e to the 5x. Okay, so I wrote this on the teacher page, but this question was on last year's linear algebra test. And this span question involves taking these two exponential functions, which are continuous functions, and looking at its first and second derivatives and linear combinations of the first and second derivatives. We have not done that yet. So at this point, what I would expect you to be able to understand is thinking about the span of these two functions just geometrically, okay? Whether we get to the rigorous proof of the span of exponential functions as a basis of R2 is something we may or may not get to. I think last year I may have jumped around a bit based on someone's, I think I jumped to that technique based on someone's question, tangential question. In any event, if you have these two functions, e to the x, e to the negative 5x, I graphed them here. If I find the linear combinations of these two, is it safe for you to see that the linear combinations of these two, of all possible linear combinations, allowing for C1 to be 0 and C2 to be 0, for example, would equal a set of functions that occupy or span R2. Okay, and you can even use the idea today of multiplying one function by a scale of the other. Okay, that's fine, because that method here that I showed you with the polynomials and taking the coefficients, we know how to find the span of polynomials rigorously. When it comes to other functions beyond polynomial functions, like exponential functions, to find the span rigorously requires something we have not done yet. Because the question of how do you create a linear system when your functions are exponential, and how do you then capture all possible results or linear combinations of those, that's a question that remains unanswered. So I just gave you this to think about. But for the problem set, for the test last year, we did do that rigorously, but you will not for the test that you have on Monday. Okay, how about this? I promised you that I'd practice some span with you. On page 201, why don't you do 14? 14 says f equals cos squared x, g equals sine squared x. Which of the following lie in the space spanned by f and g? And I'm going to even add this. If one of those, or three of those, or two of those, or all five of those lie in the space spanned by f and g, I also want to know what the values of the scalar factors C1 and C2 are. Okay? So, for number 14, let's start doing this. One element, u, is called cos squared x. Okay? And v, they call it sine squared x. It looks like here they call it f and g. Fine, same thing. And the question is, part A is, does cos 2x lie in the span of u and v? U and v. Well, the answer is yes. Is there a possible linear combination of these two, u and v, that becomes cos 2x? The answer is yes. Cosine of 2x, oh my gosh. 1 times cosine squared x minus 1 times sine squared x equals cosine double angle. Here, C1 equals 1, and C2 equals -1. So yes, cos of 2x does lie in the span of u and v. How about B and C, D and E? Go ahead and try those and replay me for the answers if you would like. Okay, so for B, C, and D, B, C, and D, oops, I have a wrong D. Oh no, this is E. This is E, and then D, I didn't even see it until now. D is sine x. Okay, so let's take a look at these, B, C, and D. So the answer for is 1 in the subspace? The answer is yes. I showed you how. Is 0 in the subspace? The answer is yes. I show you how with these choices of C1 and C2. C1 and C2. B, I am going to do it out with you. The question is it possible to get a combination C1 times cos squared x plus C2 times sine squared x? Is it possible to linearly combine these and get 3 plus x squared? This one requires a little bit of thinking outside the box. When you find a linear combination, right, what we're trying to search for here is C1 and C2. And the choice for C1 and C2 is true for all x values, correct? Like look down here. C1 and C2 are 1 and 1 no matter what x is, the angle is, right? Cos squared x plus sine squared x equals 1. I'm going to use that just to do some kind of mental math and just thinking about it and using some convenient values of x. Is this even possible? Well, let's see. Let's just play with this idea of x for a second and the fact that I know convenient values of cosine and sine at certain angles. I will choose x equals 0, okay, because it's easy. If x equals 0, I'm curious, if x equals 0, what happens is I will get C1 times 1, because the cosine of 0 is equal to 1, plus C2 times 0, sine of 0 is 0, equals 3. So this one tells me that if I let x equal 0, I have a possibility with the constant 1 equaling 3, okay? Which is interesting. Now, let's try something else. Let's just see if I can figure out what C2 would be. Well, the idea of angles here is very comforting to me. I'm going to use another axes angles. Let's see, x equals pi. X equals pi. Or pi over 2. Would pi over 2 work? Let's see. Well, I want to try and get let's stick with x equals pi. I'm choosing these values of x because I'm going to see if I find a constant value for C1, right? If I can find a constant value C1, that will make this equation equal to 3 plus x squared for all values of the angle x. I could have chose x equals pi over 2. Let me just tell you what I was thinking. I could have chosen x equals pi over 2. But when I plug in pi over 2 for x, this whole term will zero out and I'll get a C2 value, which is all well and good, but that would be very tempting for me to then walk off and say, oh, I found C1 and I found C2. C1 equals 3 and C2 equals whatever value that is over here. I think it would be 3 plus pi over 2 quantity squared, right? What I want to do is pick another value of x to see if I get a contradiction for C1. So if x equals pi, I'm going to get C1 times -1 plus C2 times 0 plus, equals 3 plus pi squared, which then tells me that C1 equals negative the quantity 3 plus pi squared. Okay, well, C1 can't be two different things. You can't have a contradiction. C1 and C2, the point of finding a linear combination is to find, right, the values of the constants that allow me to linearly combine. So this yields a contradiction. So the answer to this question is no. 3 plus x squared is not in the span of u and v. Okay, and I think there's one more I have to do. Sine x. Okay, very good. Sine x. So sine x, the question is it possible c1 times cos squared x plus c2 times sine squared x, is it possible for that to equal sine x? Okay, so I'm going to use, let's see, what can I use? I'm going to use a convenient value for x to input in. My goal is to find a contradiction. Let's see. I think I'm going to do x equals pi over 2 because sine of pi over 2. So let's check. Let x equals pi over 2. And I get c1 times 0 plus c2 times 1 equals 1. Therefore, this tells me c2 equals 1. And again, I want to try and find a contradiction. Let me show you how I plug in a not helpful value for x. And let me tell you what I mean. I worry that I talked about that too quickly. Okay, my point I was making above is that, see how I chose x equals pi over 2 and x equals 0 in order to find possible values of c1 and c2? Because a linear combination, when I have those constants, it has to be true no matter what x is, right? When x equals 0, I get down here and I get c2 times 0 equals 0. I get c1 equals 0. It would be very, very easy for me to say, yes, it is a linear combination because c1 equals 0 and c2 equals 1. The problem is that you've not checked enough. To say c1 equals 0 and c2 equals 1, this is obviously wrong, because go over here and check. Watch. If I do 0 times cos squared x plus 1 times sine squared x, right? This equals sine squared x. It doesn't equal sine x, which is what we're trying to obtain, right? And in me doing this, I'm trying to find a contradiction. I'm going to let x equals 3 pi over 2. X equals 3 pi over 2 when I input this into here and here. So x equals 3 pi over 2, I get c1 times 0 plus c2 times 1 equals -1. And c2 here equals -1. Once again, another contradiction. Okay, so no, there is no linear combination. So no. Sine x is not an element of the span of cos squared x and sine squared x. Okay, goodbye.